Um, Hello, everyone. CS205. Ray asked me to show something here, present some stuff about non-blocking algorithms and lock-free algorithms. So I'll talk about them today. Um, do you hear me okay? Okay, cool. So before that, homework 3, sorry, is due this week. And actually, you've got 2 late days, so you know.
So does the 18th include late days or does it not?
No, you get a.
2 days plus whatever the PDF says.
Okay.
I think the PDF says the 18
So
in the beginning.
Friday with the late.
Yeah, basically. Yeah. Homework 2 pull request reviews were sent to you guys. Please let us know if you didn't get a pull request review, because this means that we haven't seen your submission, and so you won't get graded. And so please let us know. One other thing is about final projects. You should have met or should meet sometime like very soon with your TF at least once, and maybe have a weekly meeting or something like that. So yeah, maybe we just want to be on top on the projects to see that progress is okay. So today we'll talk about non-blocking algorithms. So we're going back to the multi-core world. It's been a few weeks since we've talked about multi-core. And so in the multi-core world, threads may execute different code or some code, unlike the GPUs that we've seen recently. So each thread can run independently, can run whichever code it wants, and they all share some memory and can communicate by sharing this memory. And each thread can run on a different core, and we want to exploit that. We want to take advantage of the multi-core machines that we've got these days. And one of the problems that we have is that we can't actually control which thread runs which code when. And this is basically something that the scheduler of the operating system takes care of. And we cannot say explicitly, okay, run this code and then run this code, unless we use some synchronization mechanisms. Please stop me if you have any questions. So in terms of synchronization, when threads want to access the same data set, and one wants to write to that data set and one wants to read from that, then what we have something that's called a conflict or a contention on that shared resource, shared memory allocation. And so what we need to do is synchronize the accesses of the threads. To do that, what we've seen in this course is basically the typical solution is using locks. So we'll have a lock around that critical section that accesses the shared memory. And each thread, this is how we synchronize the execution of the threads. So let's take a simple example. So let's say we want a function that returns a unique integer starting from 0. So every time we invoke that function, we get a new number incrementing from 0 up. So let's assume that we have a global variable named count. It is initialized to 0. And then this is our first take on this function. It's called getNextInt. So in the first line, we just read count from the global memory to some local thread local variable called TMP. And then we increase the temporary variable by 1 and store that value into count, and then return temp. And so as you've all seen, this code is problematic if we don't have locks, if we have multiple threads that run it. Why? Why? Simple, yeah.
Does count be accessed simultaneously by multiple threads?
That's true.
Or you're not guaranteed that it can sequentially?
That's true. Count can be accessed by multiple threads. And this is actually, yeah, this is part of the problem. But the problem is that if 2 threads execute line 1 together, then both of them read count at the same time. And both of them get, let's say, 0. Okay? And then they store in their local temp variable 0, and then increase count by 1, and store 1. Both of them store 1 into the count variable, and return the TMP variable, which is 1. Okay, so this is a problem. So how do we solve it with locks? We basically add these lines of codes. So we first acquire a lock, and then we do our critical section code. We release the lock and return the variable. So the locks ensure us that those threads will be synchronized and no one will access count before it increments it. Okay? Cool. The problems with locks is that they have a few. One of them is that we've already seen is a deadlock. So let's assume that we have two threads. The thread 1 wants to acquire the lock of A and then acquire the lock B. And the second thread first acquires lock B and then acquires lock A. So you've already seen that. So if thread 1 executes lock A, then thread B execute lock B, and then thread 1 wants to execute lock B, so it tries to acquire lock B. But what's the problem? The problem is that thread 2 already acquired lock B, and so thread 1 stops and cannot move forward. And now when thread 2 executes lock A, it also stops because this lock is already acquired by thread 1, and we've got this deadlock. So you've already seen that. Another type of disadvantage that we have with locks is actually live locks. So for live locks, let's look at the code execution. So let's look at thread 1. Thread 1 first acquires the lock for A, and then many systems now support this try lock, which basically just attempts to acquire a lock. And if this attempt is failing, then it just says, okay, I could not acquire a lock. What do you want to do? And so this is basically the try lock. So then thread 1 tries to acquire the lock of B, and if it's unsuccessful, it unlocks A and retries the entire process. Well, again, lock A, then try to lock B. If not, if it's unsuccessful, unlock it, et cetera, et cetera. So both of them do that. Yeah.
Does a live lock take up a lot of resources if you're like continually cycling?
Yeah, I'll talk about it. Yeah, sure. Yeah. So what's the problem that we have right now is this. So thread 1 will try to acquire lock A. Will successfully acquire lock A, and then thread 2 will acquire lock B, and thread 1 will try to acquire lock B, and it says, okay, thread 2 already acquired it, so I cannot do that. I'll unlock A, and I'll retry the entire thing. And then it, again, locks A, and then thread B tries to lock A. It cannot. It unlocks B, and then retries, et cetera, and it goes on and on. And what's the difference between a live lock and a deadlock? In a deadlock, none of the threads can run. So if you look at the amount of resources that are used on the CPU, you'll see that nothing is being used. Nothing is executed. CPUs should be idle. But if you look at a live lock, that they're always progressing. It's called progressing, but doing nothing, basically. They just try to lock it, unlock, and et cetera, and going on and on. Okay? So this is another disadvantage of locks. And there's also priority inversion that we've briefly talked about. And so let's assume that we have two threads now. Thread 1 with a low priority and thread 2 with a high priority. This is essentially something that came from the real-time operating systems and real-time code. Those problems, this problem. But it also happens on other everyday OS. So both of them try to execute actually the same code. They acquire the lock of A, do some code, and then unlock A. So what will happen is that if we let thread 1 first run, although it's with a low priority, let's say that thread 2 is not running it yet, and then thread 1 tries to acquire lock A, successfully acquires it, then runs some code, and now thread 2 starts execution with a higher priority. And now in many of the operating systems, if a thread with a higher priority wants to run, it is all the other threads, the ones with a lower priority, are being suspended, and this thread is being run, and so it now tries to acquire lock A, but it cannot acquire it because it's already acquired by thread 1, and this is basically something that's called priority inversion, and they cannot continue just because thread 2 has a higher priority than thread 1. And also, many of these algorithms are not fault tolerant. So again, let's assume that we have 2 threads. We don't care about their priority at the moment. We care about lock A. They both try to acquire lock A and do some stuff and then unlock lock A. And so let's assume that thread 1 attempts to successfully acquires lock A, does something, and then unfortunately it crashes. Okay? So it crashes. It already acquired lock A, but it crashes. Lock A is acquired. And now when thread 2 wants to acquire lock A, it cannot proceed just because it was acquired, but thread 1 was crashed, was already crashed. Okay? And so we want something that will be able to get around all those problems. Maybe not the live lock, but we'll talk about it later. But basically, let's say that the thread crashes. We want to let the other threads also continue their work. We don't want to get the whole system suspended. So this is the idea of non-blocking algorithms. But there are a few alternatives to locks. First alternative is, okay, let's do everything in a single thread. And this works if you can get your algorithm to work with in a single thread. Just optimize it and optimize it and optimize it again. We talked about it by memory accesses and doing all sorts of stuff. Then you can get it. You can get a better performance. But unfortunately, there are two problems with this approach. First, you cannot always get your algorithm better, faster and faster. And the second problem is that if you've got, you actually don't take any advantage of the multi-core that you've got in your machines, and so you might need to do this in a different way. Sometimes there is a way to rewrite the entire algorithm to avoid locks. However, it's not usually possible. And so if you want to use the multi-cores that you've got, the multiple cores that you've got, you basically need to use advanced hardware primitives that we're going to talk about right now. So these primitives are usually called the read, modify, write operations. And it's basically a class of atomic operations. The way it works is you do something in an atomic manner. You read a single value from memory, from some shared location, and then you write a new value on top of that according to some output of a function. You might get another variable and compare it or do something. However, these are the atomic operations that we've seen, such as atomic inc and atomic add that we've seen in the GPU world. But I'm going to talk about them in the multi-core world, which in this sense they're more applicable in the multi-core world than in the GPU world, actually. So one of the problems is that these are atomic operations. These are hardware primitives that are tailored to a specific function. It's not some general function that we can get, like a big function, run it over some data, and say, okay, we want to atomically do this thing. But we'll talk about. Actually, I'll talk about this on Friday. I'll talk about transactional memory. There's a new type of functions, primitives that can help us do this large functions and do them atomically. And these are usually, most of these read, modify, write operations are usually implemented using some cache coherency protocols. So I'll just talk briefly about that. So those read, modify, write instructions are usually much more expensive in terms of cycles than a typical read or write to the memory. But how do they work? Basically, in the old days, what they did is basically they said, okay, we want to do something atomically. We'll just use locks. We'll lock everything, and then we'll execute our code, our small function, and then just release that lock. But these days, they move to something more sophisticated. They're cache coherency protocols. that basically says, okay, each core, we know that core A and core B are on the same machine. They both have their own caches, and they share some other caches, but basically they can access the same memory. And so whenever we want to execute this read, modify, write operations, let's say atomic inc, to atomically increment something, we'll just look at if core A wants to execute that operation. So first it fetches the data from memory, but then if it wants to atomically increment it, then it can look at all the other caches of all other cores, and if it sees that no other core has that in that cache, then it basically can increment it and send a write operation to the memory, and that's it. It doesn't need to take care of any other thing. So basically, we stop it in some protocol that basically talks between the caches. So let's look at an example. This is one of the most, let's say, useful primitives, read, modify, write primitives. It's called compare and swap, or compare and set. And it performs this code atomically. So it first gets an address. This CAS operation, compare and swap, gets an address, an old value, and a new value. What it does atomically, it looks at the contents of that address. So if that address is, let's say, 1,000 in memory, it looks at the contents of that memory address. And if it's equal to old val, then what it does, it atomically replaces the contents of that address with the new value and returns true. Otherwise, returns false. There's another type of this function that instead of returning true or false, it returns the old value. But I won't go into that. So basically, this is done atomically. So if your thread runs this code, it is assured that no other thread can, between the if and and adding the new address, and storing the new contents in the address, it is ensured that no other thread can run and do any other operation on that memory address. Okay? Unclear, yeah.
How does it check cross caches based on that code?
So what they do is basically if your thread wants to execute this, then it basically accesses the memory location at the address that is given here. Okay? So if your core is the only one that has this in its cache, then it's ensured that no other thread that runs on any other core will access that memory location. Okay? And so for a brief moment of time, it's ensured that no one else will access it, and then you can store that value. You can read that value and store that. Well, if it's equal to the old value, then it can store the new value. Okay? Now, what if someone else has it in its cache? Then basically you're saying, okay, someone else has it. I need to somehow decide which core has the recent value and is the one that needs to do this operation, and just do the lock. But when you're doing the lock between the cores, you're doing it between two or a few specific cores. You don't do this on entire. You don't send something on the entire bus to all the cores or something like that. And so they can get it to work much faster than what they used to in the old days. Okay? So there are other examples in the multi-core world. They're called fetch and add, which is basically atomic add. There's test and set, which basically takes a single bit and checks if it's set or not and sets it. And we won't talk about them, but just there are a few more. Yeah.
Basic question: is this something that basically happens in the background, or is this something you do?
This is basically, you just call this function CAS, compare and swap, and that's it. And it's implemented. You don't care how, actually. It's implemented in the hardware and in the CPU. And you run it, and you just know, well, as in any other function that you use. For example, in Python, do we know how, plotlib works? Like the functions show how does it work? No, we don't know how it works, but we know what it does. So basically, you need to know what it does. Okay? Yeah, sorry.
If you're doing this all atomically, why don't you just use an atomic int?
Atomic int. So atomic int, you like in Java or stuff like that? Yeah. They're basically this. They're basically implemented with these primitives. What I'm talking about is not Python actually. It's something more general. This is what you've got on the CPU. This is CPU instructions. So in CPU instructions, you basically just have load from memory or store into memory, or move between memory locations, stuff like that, or increment something, do something with the ALU. But you also have these hardware primitives, CPU instructions that give you more sophisticated atomic operations, okay? So all those atomic int and stuff like that, they're all implemented using these hardware primitives, okay? So as we said, what we care about is usually how we use that, not how it is implemented. And so let's look at the previous example that we have that we want to increment an integer starting from 0 and retrieve the old number. This is basically something like a ticketing system that when you go to, I don't know, some pharmacy or you look at some line and everyone takes a single ticket. You want to get that everyone will get a different number starting from some number, from 0 in this case, and incrementing up. And so how can we do that with the CAS, with the hardware primitives? So right now, we just read the contents of count into TMP, into the temp variable, and we do this while operation. So let's look just at the CAS. So the CAS says, let's take the address of count. So look at the address, the contents of this address, which is basically the number that is stored in count. Compare it to the old value that we've given here, TMP. And if it's equal, then atomically switch that value to this value, TMP plus 1. So if this is successful, we just continue. And we move here, and we just return the TMP. If not, then what we do, we read the count again into TMP, and then re-execute that operation. So, yeah.
What is an example case where it doesn't pass the test?
That's a good question. So let's talk about when doesn't it pass the test. So if you've got two threads, thread A and B. Thread A does this line, okay? Both of them do line 1. So both of them read count. Let's say count is 0 at the moment. So both of them read 0. Now let's get thread 1 to work, and it performs this line. When it performs this line, it goes to count. It sees that, and it says, okay, change it from 0 to 1. Okay, this is the first thread. From 0 to 1, and this is done atomically. So it checks, this operation checks that the contents of count is right now it's 0. It's equal to 0, so I'll change it to 1, and I'll just continue because it's successful. Now, when thread 2 comes and runs, and it continues execution, so it reads that, and it tries to change the contents of count from 0 to 1. But the contents of count is no longer 0. It's 1, right? And so this will fail. It will return false. We will read the new value of count. So right now it's 1. The new value in the global memory is 1. We read it into TMP, and then we re-execute that line. And now count, we compare it with 1, and if it's equal to 1, if the contents of count is 1, then we increment it to 2. And then this is successful. Okay? So, yeah, sorry.
So then when does this return 1 then?
Sorry?
You're returning TMP?
Yeah, I'm returning TMP. So the first thread will return 0, and the second thread will return 1, right? Because this is the value that we read before we incremented it. Okay? Yeah.
So in that TMP equals count line, you don't need to use an atomic operation to do that?
Reading the value here?
Sorry,
The second one. Okay. No, I don't need to do that. Why not?
Is that because if it ever got the wrong value, then it would fail the while loop again, and it would just keep updating until it gets the right value?
That's true. Whenever it reads the wrong value, or a value that will be changed by another thread, right? So it will fail here, and we will be able to reread that and try to cast again. Okay? That's a good question. Okay? More questions? So this is the cast operation. And let's look at some more data structure example. And so let's look at the stack data structure. What is a stack? So a stack is basically a sequence of elements that we've got. We've got the bottom of the stack and we've got the top of the stack. Actually, we only need the top of the stack. And it supports two operations. The first operation is push. Push with a value. It just adds a new element to the top of the stack. Okay? With some value v. And we also got the pop operation, which basically removes the top element from the stack and returns it. And now the top is basically the element after that. So far, so good? Okay. So we'll look at some algorithm that was implemented by a guy named Treiber's algorithm. And so, yeah, he worked in IBM in '86. They had a new CPU, and they were all excited. And they said, okay, we actually support this operation. It wasn't CAS. Well, the algorithm that I'll show you will be CAS, but he used another operation for that. And so we will use a linked list-based stack. What is a linked list? Sorry. So basically, you've got those nodes, those links, and each one of them has two values. One is the value itself that it stores, and one is the address to the next element. And so here we've got a stack or a linked list of two elements. The first element is the green one, holds the green data, and the next address points to this element, and here it holds the yellow one, and the next element points to something that's called null or ground or something that is basically the end of the list or the end of the stack. Okay, so if you've never seen linked lists, this is how they work. And we've got a shared top pointer for all of the threads. So right now it points to the top of the stack, top of the list. So far, so good. Okay, so let's look at the push operation. So if we look at the push operation, it works as follows. It gets some value, a val that we need to push to the stack. We first create a new element, which is basically these two stuff, the data itself. We just put the value inside, and the next address. And we do the following stuff in a do-while loop. So first we read top into old, into our local variable old. We set new next to be old. So we take the new element that we've got. We set its next address to the old that we've got. And we do a CAS operation trying to replace top, if it's equal to old, to the new address. So let's do this in steps. So we first read as we said, in the while loop, in the do-while loop, we first read the old top, and we store it in some variable old. We set the next of our new element into this one, to the previous old. And we atomically try to switch top from old to new. Okay? Okay, so let's look at the pop operation, and then we'll talk about when can it fail, when the CAS can fail, and stuff like that. So the pop operation works as follows. It first checks if top is null, which means there are no values in the stack, so it just returns null. Otherwise, it does the do-while loop, this following do-while loop. So it reads top into old, sets the new value to the old next, and atomically tries to switch top from old to its next, and returns the old value at the end. So if we look at this, basically, if we got this stack, then old points to top. This is the first line in the do-while loop. New points into old next, and we atomically perform the cas operation in order to get it out. Yeah.
So looking at push, it's clear that's going to push onto the stack correctly.
Yeah.
But there's no guarantee of like what order the different processes are pushing onto the stack, right?
Yeah.
So what does the stack really mean in that case? Is the purpose of the stack that you like first in, first out, but you don't know what's going to go in first, or sorry, first in, last out.
Yeah.
But you don't know
Last in,
what
first out.
order
Yeah.
it's gonna go in.
So yeah. So okay. So stack is last in, first out, as you said, and you don't know in which order it's working. Basically, if you've got, let's say you've got, sometimes you've got this scenario. Let's say you've got one thread that pushes into the stack, and like 5 threads that try to pop from it. Okay? Let's say it's basically some kind of producer-consumer problem. You've got one producer that just pushes more and more jobs into that stack. And you've got a few of them that tries to read them and execute them. Okay? So how can you ensure that those 5 or whatever poppers will only pop different different values and not the same value? If you don't have this kind of blocking or non-blocking algorithm to do this, if you've got something without locks and without these primitives, then you basically cannot ensure that they all read different values. Some of them might read the same value. So if you've got like a stack of jobs, then some of them might perform the same job, and you want to avoid that. Okay? Yeah.
In the code, we should just put the address of that, right?
Sorry?
It should be the address.
Oh, yeah. It should be the address of top. Basically, it's the...
Because we were assuming that it doesn't really know what is in it. Right?
Yeah. So, yeah, in this example, the original example was top. Top is basically a pointer.
Yeah.
And so we don't care. You're right. This should be the address of top. Basically. Yeah. Okay. So when can this fail? When can these cas functions fail? So these cas functions can fail if you've got, let's say, 2 pushers that push at the same time, or 2 poppers that pop in the same time, or one that pushes and one that pops, and it's all at the same time. So let's just look at this, for example. So when can this fail? So we read the top value here. We set new next to old. And while this cas fails, so when can it fail? If the old value is no longer pointed by top, right? How can this happen? Let's say some other push happened, and so the top was changed to some other value. And so this will fail. So what happens if it fails? We retry it. We read the top value again into old, set the new next to that previous element that we've got, and then we perform the cas again. Okay? So this is, for example, you can actually look at this. It's the same thing for the pop operation. So if someone pushed or popped an element after we read the top value into old, then our cas will fail, and we will need to retry the operation. So far, so good? Okay. So this is very nice, because let's say that some thread executes a push and crashes somewhere here in the middle. So what happens to all the other threads that run this code? They don't care, right? They don't care. They can continue running. We don't do any locking here. We don't use any locks. We won't have any fault-tolerant issues. We won't have any deadlocks here and stuff like that. And it's very, very nice. We will have something that is similar to LiveLock, but we'll talk about it soon. Okay? So I'll ask you a question. How can we add, let's say we want to add a new function to this data structure. In addition to push and pop, we want to run a new function that's called size, which will return the number of elements in the stack. So how can we do that? This is actually a tricky question, because what we would usually do when we've got a simple data structure, even with locks, what we would usually do is we'll add another variable, for example, in addition to the stop variable that says where's the top of the stack, we'll add another global variable called size or count, okay? But what is the problem if we'll add another variable here? So the problem is that, let's say we want to increase count here somewhere, and the cas fails. If we increase count, we can either increase count or change the top value. We cannot do both of them together. That's basically one of the limitations of these operations, that basically they work on a single memory location, as we said before. They don't work on different locations. And so if we've got different locations, we need to think of another way to execute our code, to design our algorithm. And this is not very easy. So I won't give it an answer to this. You can think about it. You can do some tricks with this data structure in order to add somehow the size into it. But not now. So far, so good? Yeah, sorry. Sorry, say again? Mm-hmm. Yeah, it can work. You're saying let's do some dereferencing. Basically, you just create another structure that points both to the top and holds the size. This will work, yeah, definitely. And you'll just change that structure every time. It will work, yeah. So the nice thing about Travers' algorithm is that it's non-blocking, and so it doesn't suffer from most of the locks stuff that we've seen. It does suffer from live lock, but we'll talk about it soon. But it also has some kind of poor scalability, because the cas, if all of them execute pop and push at once, it's basically one after the others. You cannot get more than one after the other here. There are new algorithms that basically try to take this and say, if we see that many of them fail, then we can get all of them together, all the failed operations together, put them in a single list, combine them together, and just execute them with a single cas operation, and all sorts of techniques. But yeah, these are nice to have, but not in this lecture. So there is another problem with this, with these read, modify, write primitives. It's called the ABA problem. So I think one of the best ways to explain this is, let's say we're driving a car and we stop at a red light. We look at it. Okay, this is a red light. So let's call this state A. And then we look away just for a short while. I don't know, your kid in the back. That's a wrong example. You look at your phone, let's say, okay? You look at the phone, okay? Or, you look somewhere else. And then you look back. And you see that it is still a red light. The question is, what happened in between, right? It can be that it just kept being a red light and nothing happened, like no other state was changed. Or it can be that it might have changed to green while you were looking away and changed to red again, right? So this is the idea of the ABA. You've got a state A, state B, and state A. And you don't know if it changed or not. So you don't know if you were still in state A or it changed to state B while you were looking away. So this is basically can happen in the data structures that we've seen before, the stack data structure. So how can it happen? So let's look at this example. So these are the pop and push operations that we've seen before. And let's assume we've got two threads, thread A and thread B. And thread A starts with executing a pop operation. Okay, so pop operation tries to pop the first element. So, and we've got the stack with these three elements, the red, the green, and the orange one, and this list. So the pop operation of thread A executes just the four steps, the first four lines. So it checks that the top is, if it's null, it's not null, so it just continues with a do while loop, sets the old variable of this local variable of A to the top, and the new one will be the next one, the green one. We'll point to the green value. Okay, and now let's say that thread A stops working, looks away, yeah, and thread B starts working. It performs a pop operation, and this pop operation successfully returns. There's no contention here, so returns the first element, the red one. And once it returns it, so this element is now free and can be used for any other purpose. Okay? And now it continues, thread B continues, does a pop operation, and it also successfully reads this entire thing and pops this green value and refrees that element. And now let's say that it tries to execute a push operation. So when it tries to execute a push operation, the first line of the push operation is basically create a new element. But let's say instead of creating a totally new element, we actually get something that is in the same memory location of the red one, where the red one was. And so, and it successfully, and there's no contention here, so it successfully changes the top value to this blue element, okay? And now what happens is that if thread A resumes line 5, what does it see? It sees that CAS, it tries to operate a CAS operation between top, which points to this value, the blue one, and compares it to old, which is basically the same thing. But now when it changes it to the value of new that it has. And the value of new is basically this green thing. And then we get into some state, which is basically we're pointing to some value to some element that was already freed. And this is when you usually get something like a segmentation fault, stuff like that. So there are ways to get around this. There are a few ways. One of them is called hazard pointers, basically somehow making sure that all other threads don't access your own pointers, or some pointers list that is only for you. But we won't go into the details of that. You can actually read about it. It's nice algorithms to have. Other possible ways is just basically saying whenever we free some memory location, free some memory element, what we do is basically put it in the list and just wait, well, few thousands of cycles until it's clear again. Actually millions of cycles until it's clear again and we can use it. So there are other ways for that, but we won't go into the details here. Okay? So there are different progress guarantees of these algorithms. That we can, in the literature these days, there are various non-blocking algorithms, and they're usually split between three progress guarantees. One is the wait-free algorithms. The second is the lock-free algorithm, and the third is the obstruction-free algorithm. So the strongest progress guarantee is basically the first one, the wait-free algorithm, which basically says that any operation that starts of any thread must finish after a finite number of steps, even if that thread is somewhat stalled or crashed or I don't know what. It performs some line of code, and then we are ensured that the operation will complete in a finite number of steps. So these are the nicest algorithms that you've got, because basically they don't have any of the stuff that we've seen, any of the bad stuff we've seen for locks. For example, there are no live locks here. There are no deadlocks. There are none of these. But basically, each of these algorithms is basically a paper in a nice conference or a nice journal, and they work quite hard to prove their correctness. And sometimes I've seen it like, a group of researchers, well-known researchers, publish some algorithm, and other reviewers look at it and say, wow, that looks very nice and looks okay. And then they find that, after the paper is published, they find that there is a problem in that algorithm. So they are very, very hard to prove correct, but they're very nice to see. We won't see any example here just because it will take me much longer to explain these algorithms. The second category is the lock-free algorithm. So a lock-free algorithm ensure that at least, so when you've got a few threads, one of them must finish and after a finite number of steps. I don't know which one, but one of them has to finish. Some might fail over and over again and won't be able to succeed, but we're ensured at least one succeeds. And the third progress guarantee is the abstraction-free algorithms in which a thread must complete its operation as long as there's no contention. So basically, if you've got a solo execution, some thread starts the execution, runs for, I don't know, a very, very long time, it's ensured that it will succeed. Those were introduced, I guess, like 12 years ago, something like that, when they started talking about, they started seeing that most of the time you don't actually need the log-free and wait-free in practical applications. And so abstraction-free algorithms started to be interesting. Yeah?
So in practice, how are these used? Do you basically just say, this piece of the algorithm is wait-free, so it's a wait-free algorithm, and you don't need logs or something?
So in practice, how are they used? So in practice, you either design a wait-free algorithm or a wait-free data structure, or a log-free or abstraction-free, and you say, okay, this is the data structure that I have. Anyone else can use that, right? And so, and what it is ensured is that let's say you need a linked list that is wait-free, there is a wait-free linked list. You can use it. You can do whatever you want with it, and you're ensured the threads that execute the linked list operations, they won't block. You're ensuring that all of them will finish their execution after a finite number of steps, and without trying to design this. So if you look at the usage example, so it's basically just using any library or data structure. Okay? So let me ask you a question. If you look at the, I'll go back. If you look at the at this algorithm, is it wait-free, is it log-free, or is it just abstraction-free? What do you think? Well, let's start with is it a wait-free algorithm? As we said, a wait-free algorithm must ensure that every thread must finish its execution after a finite number of steps. Is it the case here? No. Why not? Depending on others. Yeah, it's always depending on others and other threads. So why not? Let's give an example. Let's say thread A tries to push a value. Okay, it reads all the top into the old variable, and then thread B comes and then does the push operation instead and succeeds. If B succeeds with the push operation, and what will happen to A? It will have to try again. It will fail here. But if it tries again, reads the top, and then thread B comes again and executes the push operation, and so thread A will again fail, and go and so on and so on. And so we're ensured that one of them. Why are we ensured that one of the threads will succeed? Because either here or here, the cause operation works on a single element, and if someone succeeds, then if someone fails, it means that someone else succeeded in changing the memory address of top. And so one must. This is basically a log-free algorithm, and it's ensured that one of them will continue. So to sum this up, log-free algorithms are nice and can be very useful if you want to avoid logs and all their shortcomings. However, they're tailored into a specific data structure, and this code is actually hard to maintain or change. So let's say you want to add a new thing to your linked list or to your stack data structure, then you basically need to rethink about the entire process of and the entire design of your data structure and your algorithms. And this is actually one of the easiest. Stack was one of the simplest data structures that we've seen. Try to think of a double-ended queue. It's a queue where you can push and add elements both to the head of the queue and the tail of the queue. It's getting much and much harder to design these algorithms. And these algorithms are usually actually hard to prove correct. Okay, so on Wednesday, Ray will talk about cache oblivious algorithms, and I'll be back on Friday here and talk about transactional memory, which is basically taking this and making it more general. Thank you, guys.